Welcome everyone again to the last session of the day. We have here Sam Hames and Alistair Walsh, one from the Uni of Melbourne and one from the Uni of Queensland. And they're going to talk about my favourite topic, which is machine learning. So I'll hand it over. Thanks.
Okay, so I'm Sam. I think that's all the introduction you need for me. Alistair will say some more later. We also have another collaborator from ANU, Jack Simpson, who this is his data set from his PhD project. So if you don't like it, we can blame him. First challenge for the day is setup. So you'll need NumPy, SciPy, and scikit-learn installed. If you have a problem, put up a pink sticky note and we will magically fly over there. You also need the workshop data set. There's a link to it on the conference wiki under the tutorial setup page. So just get that and stick it somewhere in your directory. Now, show of hands, who's used scikit-learn before? Okay. Who's used NumPy before? Okay. So I'm going to apologize to some of you. We may cover things a little more basically than you're used to. We wanted to do a more accessible tutorial. So if you're finding it too easy, help out the people around you, talk to the people around you. Also, don't be afraid to ask for help with your sticky notes when you're stuck on anything. So I'll just give you all some time to get set up. Let us know if there's any problems, and we'll hopefully get sticky notes to all of you. I don't know if we have enough, because I wasn't expecting to fill the room. So if you are ready, put up a green sticky note so we can at least track some kind of progress. So just for your, just so you know what we're doing, we'll be demonstrating in Jupyter and we'll have some stuff in Matplotlib. They're bigger dependencies, so if you don't normally work in Jupyter or you don't want to work in Jupyter, don't worry about installing it. If you want to follow along in the exact environment we're doing it, that's what we'll be doing. All right, can I just have a quick show of hands? So everybody's done that. Can you put up your hand if you're not ready? Sorry. If you're not ready, can you put up your hand? Did everybody get the data set from the link on the wiki? Yes? You've got it? Okay. All right, I'm just gonna, we'll do the final check. So if you can run the testing your installation lines in whatever environment you're using. So you should be able to import NumPy, you should be able to import scikit-learn, and you should be able to load the data set. If you're all good with that, we're ready to go.
Don't worry, just found it. Well done.
Yes.
Awesome process.
All right, I'm just going to give you another minute or two to make sure everybody's ready to go, because it's more fun when we're not installing software. All right, so I'm just going to explain how everything's going to work. This is an interactive tutorial, which means it's going to be lots of fun and we're all going to be really lost and hopefully stuff won't break too badly. Alistair is going to start shortly. He's going to introduce the data set and the problem we're working on and start diving into the actual content. We're going to do a quick overview of NumPy just for those who aren't comfortable with it, because in all honesty, most of your adventures in machine learning are going to be adventures in manipulating your data, not actually doing anything machine learning related. It's just going to be fiddling with shapes and sizes and formats and all those other really exciting, fun things that we all want to do. So I'll hand over to Alistair now.
I'm going to use the... Yes. How you going? My name's Alistair Walsh. My background is in cognitive neuroscience. About to start a PhD at the Florey in Heidelberg, doing machine learning on brain scans to work on stroke treatment. I reckon I can identify an iris at 50 paces, and I reckon I know the survivors of the Titanic by their first name. So we thought we'd show you a data set from Jack Simpson's research. Jack's up in Canberra doing research on honeybees because of the problem with hive collapse. It's actually a very important area of research because we don't really know why the bees are suffering. So Wonder if we have some pictures. Aha. So here's some bees. We have a control group and experimental group. Jack does mean things like feed the experimental group caffeine just for kicks. No, it's actually really serious research. He's not being mean to the bees. And in each hive, there's a queen. So we have different tags for the control group, the experimental group, and the queen. And because it's dark inside the hive, it's videotaped in infrared light, so the tags are reflective. So what Jack ends up with is hundreds of hours of video of the movement inside the hive, and that's what he's analysing to try and find insights into what's going on with the bees. He's used OpenCV to identify the tags. They glow brightly under the infrared lights, put a little box around them, and we end up with a whole lot of little images that are 24 pixels by 24 pixels. It's in black and white. There's no colour information because it's infrared. So that means we have a whole lot of little images that are suitable to read into NumPy. There's the queen. And this is a shot from inside the hive. So one frame of the video. And here is a variety of the tags. So we have a tag with a square centre for the control group and a circular centre for the treatment group. And the queen tag is no shape in the middle at all. So we obviously have a lot more images of the control group and the treatment group than the queen, because there's only one queen. But we have picked out a number of those images for the queen. So that's an idea of the type of data we have. The problem is identifying the tags. We need to know who belongs to which group. There's too much footage, too many images to do that by hand, by far. So to identify the bees, we need some type of machine learning process. Back that way. Don't have a problem with machine learning, I have a problem with using your trackpad. What is that?
Oh, so you actually want to see the code?
Right.
You do want to see the code?
Yep. Right. Okay, so in the setup, we've set you up with the libraries and you've got the data set. This is the first chunk of code, just importing NumPy and Matplotlib. If you're using the Jupyter Notebook, the magic for Matplotlib inline to show the images within the Jupyter Notebook. And we've saved the data in a NumPy format so it loads in nicely. We're going to save the images data under an images variable and the identifying labels for the ones we have labelled under a labels variable. And if I run that to show you the shape of it, the images are 24 pixels by 24 pixels, and we have 730 of them. And they're saved in a format which is unsigned 8-bit integers. And that becomes important later on when we're manipulating them. So unsigned 8-bit integers have a range of values of 255. Should I be able to go down there? Help, Jack. Help, Sam. Help.
This is the joy of not being in person to work everything out until the last minute. We love remote collaboration.
Oh, so I actually have to click on that. I can't
Yeah,
use
it doesn't
that.
actually.
Oh, right. Okay. So we now have a three-dimensional matrix with all the image data loaded in, 24 by 24 pixels. Imagine a deck of cards, with each card having an image on it, and we have 730 cards. That's an idea of what it looks like. And I'm going to load one of those images just so we can have a look at it in a variable called first image, and 3 of them into a variable called several images. And just to show the shape, the single image is 24 by 24. And if we loaded 3 in, we'd have a three-dimensional matrix, 24 by 24, but there's 3 layers, each layer representing an individual image. So again, just to remind you what they look like. So I might go back to that slide just to... So you notice we have the image in the middle, which is what we're interested in. That's what identifies the bee. Around the outside, around the border of the image, there's some black areas. We're going to crop the image to the central square, so we just have that image in the middle. Anybody want to have a go at why we wouldn't leave the border around the outside? Why we're cropping it down just so we have the... Yeah, that's going to confuse the machine learning algorithm. If we leave the border around the outside, the machine learning algorithm is going to look at that as meaningful data and look at the variability in the border and try to associate that with one of the groups. So having that there is, well, let's call it noise. You know, it's information that the machine learning algorithm is going to try and fit, but it's not actually meaningful. It's just the outer edge of the label, of the tag. So here's our code for taking the centre of the image. We're going to move in 4 pixels and only take 2 4 pixels in the rows. And same with the columns. We're just going to take 4 pixels in and 4 pixels from the end. So we've gone from an image that was 24 by 24 down to 16 by 16, which is that central image with the shape in the middle that we're really interested in. Is everybody keeping up, like people that are following along with the code? I'm moving too fast. There's too many of you. You're making me nervous. I'm going too quickly. Can somebody suggest where you'd like to go back to, just so we can keep up with the code? It'd be good if you could, if you want to follow along with the code. They are. Let me go back to loading in the data. Uh-huh.
So all the materials in that repository, if you want to look at something or if you're lost somewhere.
So I think everybody managed to download the data. Was that right? We checked that before. If you wanted to follow along, you've got the data. And this is the code to load the data in. So the data is saved in a NumPy format, so you can just use NumPy to load that data in. This step is really just looking at the images. So if you didn't want to type this out, that's not really going to affect anything. I just wanted to show you what the images look like.
Where you use the first image variable in the next one. So the first image variable then is used, so you do need that.
Yep. There's some demonstration steps just to see what it's like, but when we actually go to do the machine learning bit, it's using those original that data that we set up. So this is just cropping one image to show that we're cropping it. Okay, this next step is important. So we've got a square image. That's what we need to do is have a single row for every observation. So what we're going to do is take a NumPy array, which is really just a list of lists. So each row is an individual list. They're displayed stacked on top of each other, but NumPy really understands it as a list of lists with each row being a list one after the other. We're just going to join all those lists together so we have a one-dimensional piece of data. So we're going to reshape, giving it the number of rows. The -1 is just saying, NumPy, you're good at maths, you work that out. I'm not going to tell you how long that's going to be when we lay everything out. Make the data that shape. And so now we have 730 rows by 576 columns, or 576 features, with each pixel value being a feature. So it doesn't need to be three-dimensional data because we're not actually taking any information about the relationship between one pixel to the pixels near it. We're just taking the value of that pixel, the brightness of that pixel, so we can just lay it out like that. We're not doing anything more fancy than that, basically. So I'll just pause for a second until I notice people that are trying to finish typing. Although they may be writing emails. Okay. So when we load images in as NumPy arrays, it's great because we can do simple manipulations of the image quite easily. What you're seeing here is we can add a value of 30 to the entire image just to increase the value of every pixel by 30. Or we can reduce the brightness by 30 just by taking 30 away from every value. We can increase the contrast by multiplying by a number greater than 1, so 1.5 here, or we can reduce the contrast by multiplying by a number less than 1. So very, very simple changes. This pre-processing, you would probably do an iterative process to see whether increasing the brightness or the contrast or reducing the brightness or the contrast was making a difference to how identifiable the tags were. Another thing that's worth doing is blurring the images, which might be a little bit counterintuitive. Anybody want to have a guess at why blurring the image actually improves the accuracy? Yep. Yep. So smoothing the data reduces the things that the machine learning algorithm might take notice of that aren't really meaningful, if that's a hand-wavy sort of explanation of how that process works. So blurring the image actually increases the accuracy. We're not doing that here. Let me see if I can find that image. some way that we can see. Okay. I should have kept my mouth shut rather than promising. What about if I reduce the size? Is that going to work? Okay. No, it's not. Look, you can see a small slice on the top here. One thing we wanted to point out, when we're just adding values to the image, can you see it's gone from this to this here, where the bits that were bright are now actually black? That's related to the fact that we have unsigned integers that have values from 0 to 25. If we just add values and we go over 255, it'll scroll back around and be a very low value. So even though it's very easy to be able to add values and do simple manipulations, you have to be a little bit careful or else you can get an unexpected result. Which is that question there? So does anybody know the answer to that question? Does that make sense to anybody who...
Just the reason we put it there is because, like I said, most of the time you deal with your data, not with the machine learning model. And when you forget to do stuff like convert your integers into floats, that'll flow right through your problem and you'll wonder what is going on. Normally, the place to look for problems is in your data and your formatting and all of the data manipulation that goes before that. So this is just a reminder that types and what you expect to be flowing through, you need to verify that. Before you even worry about the modeling, worry about what your data is and what it's doing. Because the modeling is honestly the easy part.
Yep. Okay, so here's just to remind you that we have a rectangle pattern, a circle pattern, and a blank pattern. And we can't feed words into scikit-learn. We need to feed everything in as numeric values. So the labels are identified by 0, 1, and 2. We have 100 bees in the control group, 100 bees that are treated with caffeine and the single queen. So here I'm loading in the labels for each image. And printing out the shape of the labels data. So there's 730 labels to go along with our 730 images. And just stepping through the labels 100 at a time just to show you that there's zeros, ones, and twos in a sequence. So all the 0 images come first, then the ones, and then the queen ones, which are 2. So that's a very quick run through the pre-processing. A lot of the work is in getting the images to a point where you can do the machine learning on them. The bulk of the time is spent on preparing your images. Like that really is where a lot of the hours come in, trying to work out what's going to affect the success of your model. Training a model and predicting with it, scikit-learn has made really easy. So that those preparation steps are really where a lot of trial and error comes in. After we've pre-processed the images, we then need a testing set, a training set. So we need to split the data up because we're going to train a machine learning model on some data. And of course, we can get that really accurate if we know the answer to everything. But the problem of overfitting the model to the data that we've actually got and then making it less able to detect new tags. So our purpose here is to take a set of data and identify them by hand, so a supervised machine learning. Should I explain the difference between supervised machine learning, unsupervised machine learning, and neural networks? I'm not going to explain neural networks, that's a black art. But supervised and unsupervised? Yes? Okay. Basically, the idea is if I've gone through some data and identified them, so if I've looked at these tags and given it a number according to what it looks like, I'm well able to look at the tags individually and say, yes, that's that one and that's that one. That would be supervised machine learning. Unsupervised machine learning is like clustering. You're not giving the machine learning algorithm any information about which is which. It's looking at the variability in the data and what features move together to group. And we'll show you some figures of grouping of data. But basically, our problem today is supervised machine learning. We do have a set of answers, but we're interested in all the rest of the data that we haven't labelled by hand. We want the machine learning algorithm to predict which group they belong into based on that information. So we need some data to train on, and then we need some data that we haven't trained on to test the accuracy of our machine learning algorithm. Scikit-learn makes this process really easy with the train test split function. If I was just to take 80% of the data for my training set, leave 20% of the data as my testing set later on, you saw that the labels are in sequence. If I just take the first 80%, I'm going to end up with a whole lot of the control group, maybe a couple of the testing, a whole lot of the control group, some of the experimental group, and no queen. So I'm going to be training on data that is all one type. So the train test split function makes sure it gets a selection of all the different types of images that are in the data set. And it does it very easily. We don't have to write a lot of code to get a good mix of each group in the training and testing sets, so that once we've trained, we'll get a good representation of how accurate that model is when we test it. Just trying to... that last bit is random underscore state equals 4. Yes, random underscore state equals 4. That's just so we can repeat this process and get the same answers. It's a random process. If we didn't set a random state, we wouldn't be able to repeat it. And we're saying we want 80% of the data in our training group. We want to leave 20% of the data over to test on. So you can see the X-train shape, 584 observations, 576 features. When we laid the image out end to end, we ended up with 576 columns, 584 labels to go with those 584 training examples. In the testing set, that's 20%, 146 rows, same amount of features, has to be the same amount of features in the same order, so for the training and the testing set. Does that make sense? It has to be the same type of data in the same order, or else the machine learning algorithm isn't going to be able to make sense of it. And then finally, 146 labels for the testing set. Just listening for key taps. Yeah.
Is there a rule about the
There's no rule. It does depend on the type of problem you've got. We've got a problem where the groups are relatively even. You might have another problem where you're looking at intrusion detection or cancer detection where the positive is very, very rare. So this is very common, an 80-20 split, you know, given a normal problem. I don't know if there's any normal problems, but it depends on how much data you've got. If you've got all the data in the world, you know, it's like a bigger testing set would improve things, but generally you haven't got as much data as you want. You've got a limited set of data, and you want a decent amount of data to train the model on so that you get an idea of the variability. So yeah, it's a bit of a compromise between having enough data to train well, but still having enough testing data to check how accurate your model is. Okay, principal components analysis. This is a type of clustering, so a type of unsupervised machine learning. We do have the labels. This is a supervised machine learning problem, but in this step we're not using the labels. We're just going to get the principal components analysis algorithm to cluster the data and graph it for you to show you how it splits up, how different these groups are. So we import an algorithm, we instantiate the algorithm, we fit the algorithm on the training data, and you'll notice that there's a big X representing the training data. So this is a convention in scikit-learn, a big X for the training data. And then we transform X. You can do the fit transform in one step, but we're showing you there that there are actually two steps. And then we're just going to plot that clustering. So you can see half a figure there, which is great. So what we've done is plot the data on the X and Y axis and colour it according to the label. The little y is the label, so this is part of this convention of big X is the training data, little y is the labels, and a fixed size. And you can see there are three groups. Well, we've coloured them according to their group. The red ones here seem to be sitting out nicely on their own. The green and the blue ones, there's a bit of overlap. This is actually a three-dimensional space, and if we rotated it, you might see that the groups are separated on a particular axis, but not this one we're looking at. So if I was to rotate that to the right, you might see that there is a bit of space between the green and blue groups. But that's using an unsupervised algorithm where scikit-learn is just looking at the variability in the features and seeing which ones move together. I'm not really going to have a go at explaining how principal components analysis works. I have done an undergraduate psych and my statistics teacher would be ashamed of me. But we can just treat it as a black box. Principal components analysis is the process. Look that up on Wikipedia, would give you the explanation that I'm going to give you. So now we're going to try and visualise with another type of algorithm, linear discriminant analysis. This is using the labels, so it's a type of supervised machine learning. And again, it's the same process. So the scikit-learn process. Yep, I kind of expected that. This process of import the algorithm, instantiate the algorithm, fit the algorithm to the data, and then make predictions, or we're going to display it. This process is what makes sklearn really easy to use. It's the same procedure no matter what type of algorithm you're using. So your workflow is these 4 steps all the time. Of course, if you knew more about the algorithms and what they're suitable for and what they're not suitable for, that's going to make your performance better. But you can treat it as a bit of a black box and just plug your algorithm in to that spot there. Down here, really nicely separated, is the red and green groups. Oh, let me show you all the images. Right, so that was the contrast that went over the limits. Here's the one previous, the principal components analysis. And there's the linear discriminant analysis. So a good cat swinging space between the groups there. So here's a diagram of what linear discriminant analysis is trying to do. It's, sorry? That's a really bad diagram of what linear discriminant analysis is. That's really a support vector machine diagram. Linear discriminant analysis is trying to rotate the data so it can put a line between the different groups and best differentiate the groups. That was really, really hand-wavy. That was like really hand-wavy.
It's magic. That's
Yes,
what it is.
It's a magic black box. Okay, so I think we can go back to, that was a bad idea. So now that we've had a look at what these algorithms are trying to do, let's train a model and make some predictions on the data that we've left aside, that we haven't given the algorithm access to, so it can learn from that. We've given it the training data set, that's the information that it's got, and then we're going to try and make predictions on the data that we left over to see how well it goes, to see if there's enough information in the training data set for it to make predictions on data that it hasn't seen before, because this will be the problem. We'll hand label a certain number of images, but then we want the machine learning algorithm to learn the relationship between the features and be accurate at predicting the thousands and thousands of images that it hasn't seen. So we're going to import a support vector machine. We're going to instantiate that classifier, CLF. We're going to fit the classifier to the training data, big X train, and the labels that go with that, little Y train. So we have the image data in X underscore train, and we have the labels in Y underscore train. And then to get an idea of how accurate that model is going to be on unseen data, we're going to transform the X-test data Did we already load in the... no, there's the line for the metrics there. So we're going to transform the X-test data, the unseen data, and then we're going to run a prediction on that data. So we've trained the model, and now it's going to have a go at predicting the label of each of the testing rows. And sklearn also has built into it methods for testing the accuracy of the prediction. We're going to use a very simple measure of accuracy here, the accuracy score. It's just the percent that it got right. So the most basic accuracy measure you can get, which is suitable for our problem because we have examples from each class. Not suitable for all problems. Accuracy testing is a huge area in its own right. Different problems require different accuracy measures, but this one's suitable for what we're doing. And 0.69% correct. Better than a coin toss, but not great. So we're comparing this score, so 0.69 correct, with the accuracy we could have got if we just used the most common label. So if I just looked, what's the most common label, and I just said, well, they're all one, that would be a baseline accuracy measure, and this is a bit better than that, but not much. So we've got some time now for you to, if you've been following along with the code, because there's this standard process of, do we have time? Yeah. Because this is standard process of select a model, train the model on the training data, and then test it on the testing data, you can replace that algorithm with whatever else you like in the sklearn library. It takes standard inputs and gives standard outputs. So if you're following along with the code, has anybody got any questions that I might be able to answer while Sam's going to show you some fancy stuff. That was a very basic machine learning.
Yeah. Before we get to that though, fiddle around, have a look at the scikit-learn documentation, find a different classifier and plug it in instead of SVM and see what happens. So the take-home message about this part is that you only need to know you only need to know a handful of things to use scikit-learn classifiers. You instantiate an object. That instantiation doesn't actually do anything itself except set some parameters. You call fit to feed your data in. You call predict or transform to predict some values or transform some values. They all have the same methods, and you interact with them all the same way, regardless of what the actual object is. So just play around. Drop in a random forest classifier or logistic regression or something.
Naive Bayes.
Yes.
If you want to do
Good
Bayesian
one.
statistics, yep, one line, here you go.
Play around, answer those questions, and then I'll move on to the next step. We're actually, amazingly, we are doing well for time, which has never happened to me before, so I'm sure I'll ruin it later, don't worry.
Any questions? Like, I'm sure there's a whole range of different... Yes?
At this point, you just go, well, it's wasting your time, or is that a good number?
It's not a good number. Machine learning can regularly get up above 85 in the 90s. You know, that's we'd be smiling if we saw that.
I would modify that though. It really depends on your problem.
It does.
If you get 69%, but a human does 40%, that's amazing. It's always data set specific and problem specific.
Right, I guess if the problem is how do we, save the world or whatever, then 69% is actually probably pretty good because the problem is quite important.
Yes.
It's
Yes.
way better than what we can do just sitting in a room
And this is one way of looking at accuracy. Like this is just a, how many did it get right compared to how many it got wrong? There are other ways to look at it, like when it misclassified, did it misclassify in a particular way? Like a confusion matrix would tell you, is it able to identify the queens really well, but gets mixed up between the experimental group and the control group? Once you've here's one I prepared earlier.
So this is another way to look at this particular problem. So the accuracy is all of the diagonals. So if it's on a diagonal, it's correctly classified 24 of the queens, 49 of the treatment, 29 of the control group. All the off-axis ones are errors. And there's a few systematic errors where the control group is often confused for a queen. So this is another way to look at it. We probably shouldn't get too bogged down in it because there are many interesting and wonderful ways to measure it, and it all depends on what your actual problem you're trying to solve is. So for this particular case, 69% accuracy probably isn't good enough. And I'm pretty sure Jack's PhD is using something that's significantly more accurate. And we'll show you in a bit that I think you can do some fiddling, or you might find yourself playing around with some other classifiers that you'll get better performance straight away. So just maybe take 3 or 4 minutes, just fiddle around with the classifiers and we'll come around and answer any individual questions you'll have and then we'll regroup and move on to some of the more interesting parts of Scikit-learn's API in terms of making this easier and manageable. So 3 or 4 minutes, fiddle around, we'll be back.
That's probably a factor in the moment.
So the question is, what are we actually trying to do? Why are we using machine learning?
What are you actually trying to predict in this size? Or what,
We're just trying to label the bees. There's too many thousands of, well, not thousands, too many hundreds of hours of video.
based on the movement around the hive?
Yep, and the length of time that the experiment runs over. So it runs over weeks, continuously videoed. Labeling each tag by hand is not possible. So we need machine learning here, but we need a reasonable level of accuracy. If it's not accurate, it's of no use. Yeah. Well, that's the idea. Yeah, can we actually show that? But we'd have to know which bee was which bee, and then get a measure of the, you know, the next step would be, did they move more? Yeah. Did it have an effect on the queen? Yeah.
All right, so I know a few people have tried a few things out. Let's just throw one in here so you can see an example. That's not where I wanted it. So somebody did a random forest classifier. So from scikit-learn, which is in ensemble. You don't need to worry about what ensembles are. I do need to remember what the syntax is though. So we can say CLF equals random forest classifier. All of the scikit-learn models, they have default parameters set. They may not be good defaults, but they have them set, so you don't need to feed in anything to start with. Now I'm just going to fit in our LDA transformed X data, and our training labels. And I'm just going to steal this code and run it again, and we can see what happens. So just by switching from a support vector machine to a random forest classifier, we got 8% performance improvement. We're also no longer misclassifying all the queen images, which might be important for our particular problem, because maybe we really care about the queen. In many problems, one class is really interesting, all the other stuff isn't so interesting. So if we were doing a project on queen bee behavior, how well we do on the queens is probably the most important thing, and we build a scoring method around that. So for this last section, we're going to look at a little bit more of scikit-learn's API and how scikit-learn makes it actually easier to deal with all of this stuff. So up to this point, we've been doing a lot of manual data manipulation. So we've had some data, we've reshaped it, we've had a bunch of temporary variables, we've had X transform, we've had X test, we've had X train. Now we're going to use scikit-learn's API, and we're going to make it all work nicely together and in a way that is more easily maintainable, easier to think about, easier to reason about, easier to collect all of the logic of your program together. So we're going to build a pipeline. We are, too far, sorry. So a pipeline lets us take a bunch of scikit-learn or compatible objects, and we'll get to the compatibility part next. So we instantiate, so we can replace all of our previous process with a pipeline. So we have one part which is the LDA component, so we're just going to construct the LDA transformer object. We're going to construct our support vector classifier object. We're not doing, note that we're not fitting or transforming or predicting or anything at this point. Now we're going to build, from those two objects, we're going to build a pipeline. So a scikit-learn pipeline object is itself a classifier. So we're going to take all of the components of our models and stick them together into one convenient object. So instead of reasoning about all of the components of our process, we just need to worry about the pipeline object. And to fit, predict, and so on, we don't need to worry about the individual components. We just call pipeline.fit. And that will start at the beginning of our pipeline, call fit and transform on that part, move it on to the next part, call fit and transform all the way to the end. So we wrap our complex, many-stage process into a single convenient object. And what we're doing here only has 3 steps. We've got pre-process the data into the right shape, run LDA on it, run a classifier on it. But in a real system, you might have 5 or 10. Like if you're doing text analytics, you have to do a bunch of extra steps. You can't just take the raw pixel values. So a pipeline object lets you collect all the pieces, stick them into one convenient object, and reason on them like that. So what we do here, so the syntax for the pipeline constructor, it's a list of tuples or lists or whatever. The important part is that you give that stage of the pipeline a name, and then you give it the object at that stage in the pipeline. So the first thing is the first step in the pipeline, which is the LDA. The second thing is the classifier. And the names are important for a reason we'll come back to later, because if you want to inspect the components of the pipeline, you need to know what the name is. So if we run this section, our pipeline.fit method behaves exactly the same as if we'd run LDA, built a new matrix, run the support vector classifier.fit, and so on. I've also used this convenient shortcut score method, which for this classifier gives us accuracy, because I'm lazy and I don't want to type those extra lines, and it's nearly time for the conference dinner, so let's not. Just remember that score is a quick shortcut method. You may not want to use it for all problems, but it's there. Where scikit-learn becomes really good, though, oh, good. It's not a workshop if something doesn't break. There we go. So remember at the start where we said we were going to crop it and then we kind of forgot about that? Let's bring it back. So the very first stage in our process was to take the images, unwrap them, and we forgot to crop them, but we'll do it now. None of that process fits within scikit-learn's default objects. So by default, scikit-learn, every object takes an X, which is a 2D array, and a Y, which is a 1D array of labels. If you want to extend your own stuff and adapt your data sources or do your pre-processing in a way that doesn't make sense in scikit-learn, you can implement an object that fits in with scikit-learn's API like this. So you only need to do a handful of things. You need to import those two classes. They don't actually do much, but they're important for all the other stuff to work. Like I think the base estimator just has a way to copy parameters from one classifier to another and a few other bits. And the transformer mixin just has a quick method for fit transform define. That's all those do. All you need to do to write an object is, to be compatible with the scikit-learn API, is write an object that does that. That create a class that inherits those two things. Your init method is limited. You can only do variable assignment. You can't do any processing in that method, otherwise it will break other stuff when you try and use it further on in your pipeline. Then all you need to do is implement fit, transform, or predict. So you always need fit and then transform or predict depending on whether you're doing a classifier or something else. So this class is a scikit-learn compatible class. We can use it at the start of our pipeline to go from our raw images in a 3D array to the format scikit-learn expects, and then it's just going to work transparently through it all. So if we define this class, we can plug it straight into our pipeline like this. So now the very first method component of our pipeline is the unwrap class we just defined. And that's it. We now have a scikit-learn compatible class that works with all the scikit-learn's classifiers and transformers that we want to use. And all you need to do is implement a couple of methods and inherit from some stuff. That's pretty much all you need. So now we have a pipeline that goes from our raw image data in the format we had it to begin with. It implements all the logic of our transforming and pre-processing and so on. And it also does the cropping that we forgot about. And the crop pixels is a parameter to this method. So if we want to experiment with different amounts of cropping, we can do it at this layer in our pipeline. We don't need to worry about throwing around some individual, we don't need to have a bunch of temporary arrays floating around while we do our transformations manually. Does anybody have any questions up till there? Because it gets really good at the next part and I don't want anybody to be lost. Or everybody's ready for dinner. Or either way is good. So I'll just run this and convince you that it doesn't fail. So now, instead of XTransform, XTrain, all that other stuff, we started with our raw images, which are a 3D array. We can fit the pipeline all the way from beginning to end, and we don't have to worry about all the intermediate steps because we've abstracted them away. We can just think about what is this pipeline object doing and not worry about the details when we're actually using all of this stuff. Now let's make it even better. So you would have noticed that all of our numbers were magic numbers. So we set parameters for the support vector machine, C and gamma, I think. We set a magic number of pixels to crop out, and we set a magic number of components to our LDA. Using the randomized search cross-validation, which you should use, don't use grid search, use that one. You can ask me why later. The parameters you choose, the optimal ones, they're always, always, always problem dependent. You can't just pick them and say that's good enough. Well, you can if it solves your problem, but you may not have the best parameters. And most of the time you'll go in, you'll use the default parameters and you'll get 20% performance and you go, I really am gonna have to fiddle with these things. This randomized search cross-validation object lets you do it. So see here where I've used LDA _n components. For this randomized search, I'm telling it for the LDA component of my pipeline, vary the number of components, pick from those options. For the unwrap component of my pipeline, vary the crop pixels variable along these particular things. So we're going to try cropping between 0 and 8 pixels. And let's vary C and see what happens to our performance. So when we do a randomized search, the cross-validation part is it splits up the data we give it into a bunch of subsets. It trains on if we split it up into k subsets, it'll train on k-1, so one less than the amount you broke it up into, and test on the other one, and it'll repeat for all of those combinations. When you do this process, it'll give you it will choose the best scoring combination of parameters from running all of that stuff as the optimal values for your particular problem. So if we run this object, it's going to give us a principal way to choose amongst all of our different bits and pieces. Oh, yep. The default is to use stratification, but we'll come back to that because there's a more important question there. So if we run that, it's going to give us a whole bunch of really exciting numerical errors, which I think are to do with the LDA component. So if you see something like this, it means you need to investigate what's going on in your things because it may be numerically ill-conditioned. And there'll be a lot of them because I said use 20 iterations of random search to find something. So every single time we tried to run this model, it gave us a numerical warning. So that's something to be aware of. And at the end of it, we have a randomized search CV object, which itself has a predict and a transform method. So that randomized search method CV object took our pipeline and gave us something even better. So we have our whole beginning to end of our problem encapsulated in a single object. All of the logic is in there. And you only need to call fit once and predict whenever you need to predict later on. So when having fit that, we can inspect the attributes of the searcher object, and it'll tell us what it thinks the best score is out of all of those options, and what the best parameters were. And it thinks that cropping out 8 pixels was the best thing to do. It's a randomized search though, so you may get different answers every time. Now, we're going to start kind of wrapping up for this last section, but I do have some exercises for you. First one is, why is what I did there completely wrong? And why should you never ever do that in practice? Yes, don't ever test on your training set. If you do that, you get wonderful numbers that look like they're working and you go, look, it's almost perfectly accurate. Let's roll it out. No, it's really not. It's really easy to trick yourself and accidentally mix stuff up. I am speaking from experience. I'm not just telling you it's a bad idea. It's really, really, really easy. Particularly if you have time series as well, it's even harder because you can't mix past and future values together because that'll make it even worse. So if we actually repeat this process using a proper train and test split, we only get 78% performance. So that 96% you saw before, that was a lie. I mean, I know it seems really obvious when it's pointed out and in hindsight, but it's really easy to get caught up in your particular problem. And you start hunting for performance, and you think you found it. But if you find it by doing something like this, you haven't found anything. You've just tricked yourself. Yes?
Why is this better than grid search?
Because grid search is computationally inefficient, and there's a really nice paper, which is in the notes. Short answer is use randomized search as your baseline. Any more questions? I'll wrap up after if there's no more questions. If you remember nothing else, remember don't test on your training set.
What I get from that is when you're using a cross-validator, doesn't that automatically not test on itself?
Not for performance. Because we use the cross-validator to pick the parameters, we can't use the performance numbers. You have to nest them if you want to do it that way. For the rest, if that doesn't make sense to you, don't worry, we're getting ahead of ourselves. More questions, more questions. Okay. Close it, oh, yes. Yeah, absolutely. Oh, like Google's APIs and stuff, yep. It depends on what it is. If it's something like, I want you to find what's in this natural image, go use Google's thingy. You'll never beat Google at that. If it's, I have a specific business problem based on my specific business data and my specific business goals, I don't think that will be automated. Parts of it are always going to get easier and better. Like what I was talking about with the randomized search and picking different models and all that other stuff, there's already tools to automate parts of that. But you can never get, I don't think we'll ever get to the point where there'll just be an API, you send it some data and you get back meaningful predictions, except for very specific problems. But that's just my opinion, but maybe I'd like a job going forward, so I could be biased. I've got 4 pieces of advice for you. Oh, there's also the workshop repo there. If you have any questions or comments or feedback, you can raise an issue or things in the notes that you're looking back on and don't make sense. Please feel free to leave notes there. In general for machine learning, just because you can doesn't mean you should, which I know is not necessarily a well-received thing to a technical community, but it's not always the right tool for your approach. I'll just leave that at that. Accuracy is not necessarily the right metric. I can say none of you have cancer, and that is a really accurate statement. If you did happen to have cancer, that's not a very useful statement, though. Hold on, I'll rephrase that. I could state that nobody in this room has cancer. I could be 99% accurate. To the person who does have cancer, that is not very useful because you're wrong. And saying someone doesn't have cancer when they do is a really serious consequence. Whereas, number 3 is you and your data are biased, and you will never know all of the sources of the bias. So don't go and build predictive models for crime based on 200 years of probably biased crime data. I wish that wasn't a real thing, but there you go. Don't predict terrorists based on 15 examples across a population of 15 million, because, well, that was CIA. That's not really a good way to do it. I put that one in because neural networks and deep learning are a really good way to waste time. They're a really good way to overcomplicate a problem. Seriously, they're a rabbit warren. If you may find that they're useful for your problem, I would never start there. Unless you're doing something very specific about images or speech where that's the obvious way to go, don't start there. Don't feed your business problem into a deep learning thing and expect to get magically good results that are repeatable and reliable. That's it. Thank you all.
All right.